Hi, I'm Aman Mathur from the Max Planck Institute for Software Systems in Germany. I'm here to talk about our work on synthesizing constraints for parametric CAD. Parametric CAD is moving beyond the traditional domains of engineering to everyday people and hobbyists. Well, the premise is amazing. You design an object once and then just change parameter values to get infinitely many variants. Websites such as Thingiverse and more recently CAD Hub are enabling this. Sounds amazing, right? Well, the parametricity adds a bunch of complexity. People often don't know which values lead to valid results and how to find these values. Let's take an example. Here we have a design of a simple hex nut. The design is parametric, meaning this, and this can be changed to get many variations of this design. This means this is a valid variation, and so is this. However, if we increase the diameter of the hole here, we get something like this. Notice how this final object is segmented and the intended topology is lost. I, like most people, would consider this as not valid. Similarly, if we were to increase the diameter of this hole further, we would get nothing because the hole would be so big that it cuts through everything. This is also not valid. Here we have the same design but with a much longer chamfer. Notice how this large chamfer is really cutting close to the height of the nut. This object is valid. However, if we were to increase the length of the chamfer further, we would get a runtime error because the underlying object will not be able to accommodate this chamfer. So clearly, some parameter configurations lead to valid results and some do not. Let's try to collect some clues. Let's look at the sequence of operations involved and see what we can do. Now, clearly, the first step, which is making a hexagon of this diameter d, shouldn't be a problem. As long as this is greater than 0, we're good. This will not fail. The next one also does not. We just extrude this face to a height of h. As long as it is greater than 0, this will not fail. Next, we make a chamfer of the length small l. As we saw before, this cannot be arbitrarily large. And the last operation, making a hole of diameter small d, this can also not be arbitrarily large. Otherwise, we would get a segmented or empty object. To summarize, many parameter configurations here are actually invalid. In fact, if we were to sample these parameters naively, only about 11% would lead to a valid final object. Maybe we can do better. So we know that these two should be greater than 0. That's fine. But perhaps we can try to find constraints for L and D. Doing so is a bit challenging. Solving this analytically, we find that L should be less than this and this, which means that L should be less than the minimum of 0.43 times D and H. D should be less than this, which means D should be less than 0.87 times capital D. Clearly, this would eliminate all invalid configurations, but coming up with this is difficult. Let's get down to the central intuition behind our work then. We've been talking about parametric CAD, which involves a sequence of operations that use parameter values to generate an output. Some of these lead to invalid results. And as we saw, each operation gives some perspective on how it changes the underlying object. And this can be useful in finding constraints. By these metrics, parametric CAD seems a lot like traditional programs. In the area of programming, the theme of finding and eliminating bad parameter values is actually quite well explored. Parameter constraints are clearly useful, and to give you some perspective, Thingiverse encourages designers to also upload constraints to their design parameters. In fact, most popular designs on Thingiverse have these constraints. However, because the process of finding these constraints is difficult, as we saw, most designers do not specify this. and therefore most new designs do not have these constraints. Moreover, it's not just people who are exploring the parametricity of CAD. Recent graphics research has been looking at design parameter exploration to find optimal objects by some metric. As the first step of such techniques is to sample the initial parameter space, it makes a lot of sense to have constraints so that the expensive optimization technique does not spend too much time on invalid configurations. So clearly, this is an important problem. Well, in fact, we are also not the first to explore this. FabForms uses parametric designs built using OpenSCAD and synthesizes constraints for these. FabForms, however, uses physics-based checks and works on final meshes. This makes it quite slow, and it takes an order of days or weeks for most designs. The focus of our work is on geometry-based validity checks. We synthesize constraints using a mix of static and dynamic analysis. Static meaning we just get a constraint using the sequence of operations involved, and dynamic meaning we actually evaluate the design on some concrete values and make some conclusions. We use the highly expressive and widely popular boundary representation of BREP. Our analysis is always within this representation, and we're able to synthesize constraints quicker, in the order of a few seconds or a few minutes at most. At a high level, this is how our technique works. We first go over the sequence of operations and try to find constraints statically wherever possible. Once this is done, we go to the dynamic analysis part. Here, as is standard in syntax-guided synthesis, we propose hypotheses of increasing complexity. We then evaluate the design on concrete parameter values and check if the hypothesis holds. If it does not, we try a new hypothesis, and if it fits, we can keep trying to falsify it or fine-tune it until we are satisfied. Let's look at static analysis first. Some straightforward examples are making a circle, a box, or extruding a face. As we're creating new geometry here, we can constrain their parameters to any value greater than 0. Then there are some examples of operations such as counter borehole and counter sinkhole. Here, by definition of these operations, for example, we have that the inner hole diameter needs to be less than the outer hole diameter. For these operations as well, what we find is, by definition, the outer hole height should be less than the inner hole height. Now let's move on to dynamic analysis. Consider operations such as chamfer, fillet, and hole. Clearly, these parameters should be less than some value. We'll get back to this one soon enough, but we can also be sure that these are for sure less than the bounding box diagonal of the intermediary object on which these operate. Let's find this constraint now. We consider our earlier example and try to find constraints for small l here. For dynamic analysis, our hypothesis generator proposes this hypothesis. Maybe L is less than some constant times capital B. Our sampler and solver then evaluate the design on some concrete parameter values, and what they find is actually this hypothesis does not hold. Then the hypothesis generator suggests this, to which our sampler and solver also say that this does not hold. After a few steps, our hypothesis generator could suggest this, that this is less than minimum of some constant times d and some constant times h. In this case, if the sampler and solver says that, okay, this hypothesis fits, what we get as an end result through the solver is a solution for these constants as well. So we essentially get our final constraints. As you can see, this technique is quite general. However, we cannot solve for all constraints. For example, if we were to solve for f here, this f depends on the upper and the lower diameters of the circles here, but also on the slant height here, which is not given and needs to be calculated. as our hypothesis generator and solver do not support complex nonlinear or geometric functions, we cannot solve this. We tested our technique on designs from a public dataset known as the Fusion 360 segmentation dataset. Our test set had various designs with some with as many as 12 parameters and some with as little as 0.1% of the parameter space valid. For these, we were able to successfully synthesize constraints for all parameters for a vast majority of the designs. There were a few designs which we could not solve fully. In these cases, we found constraints for some of the parameters. Our technique was fast. We, in fact, only took 36 seconds on average. Finally, we were quite successful at constraining the parameter space of designs. From an average of 26% of samples being valid, our constraints enabled getting to 84% of the samples being valid. To conclude, we applied ideas from program analysis to parametric CAD. A technique for finding constraints for CAD is actually quite fast. Though our technique works for a large variety of CAD objects, we can currently not synthesize complex nonlinear or geometric constraints. Thanks a lot. Please read our paper available here for more information and try our source code available here. I look forward to your questions.